I want to introduce you to the chain rule. So the way you can think about this, this is going to tell us how to take the derivative of a composition of functions. Intuitively, here's how I like to think about it. So say you're watching a movie, and that's going to be your first function. So maybe you've got a function of time, and that's like the movie playing, okay? And you've got an old projector, so you're feeding the film into the movie, and the rate of change of the film is whatever it is, 24 frames a second, 48 frames a second, okay? And say now that you feed in the film twice as fast. So what's now the rate of change of the movie? Well, it's going to be however fast it was going times 2, because you started, feeding it in twice as fast. So, for example, say your film was like f of x equals sine of x. X is keeping track of time, and you're watching that little sine curve as time goes on. And say speeding up the film times 2, that's going to be a function g of x, just takes the time and multiply it by 2. And so the process of speeding the film up twice as fast, that's going to be the composition, f composed with g of x. So composition of functions, let me remind you, that means take your original function and just plug in g of x. So this is sine of 2x. And so when I ask you, what is the derivative of sine of 2x? That's like saying, how fast is that movie playing when you've sped up the film times 2? And the answer is, just like we said, it's however fast it was playing originally. Well, how fast was it playing originally? That's the derivative. And so the derivative of sine, that's cosine, so I get cosine. But I'm at the point 2x, so I plug in cosine of 2x. So that's the speed of the film originally, and then I have to multiply it by 2. In other words, I have to multiply it by the derivative of g of x. So we usually like to write the constants out front, so I'll write it there, 2 times cosine of 2x. So in other words, the derivative of the composition, f composed with g, is take the derivative of f, plug in g of x, multiply it by the derivative of g of x. So rates of change multiply together. So in a later video, I'll give you a proof, a mathematical proof of why this equation is true. This is called the chain rule. But here I'm just trying to explain the general idea. And another way to help understand this is restating this in Leibniz notation. So what Leibniz would do is he'd say, let's write y equals g of x. And that's, in our example, that's y equals 2x. But this is going to be true for any functions f and g, so long as f is differentiable at the point g of x, and so long as function g of x is differentiable. And then your composition, f composed with g of x, you can call that, well, that's just plugging g of x into f, so that's just f of y. And so let's take some derivatives now. So y prime, in Leibniz notation, that's dy dx. And what's the derivative f composed with g prime? This is the derivative of f of y with respect to x. So Leibniz would write that df dx. And one more thing, so what's the derivative of f, and then plug in g? That's going to be df dy. And that might not make complete sense, but if you think about it for a little bit, then it will make sense, because df dy, that's just the derivative of this with respect to variable y. That's just taking the derivative of function f and then plugging in variable y. So when you put the statement of the chain rule rewritten in these terms, what you end up with is df dx on the left-hand side, that's equal to df dy times dy dx. Let me bring it home by doing this with the example with f of x equals sine of x and g of x equals 2x. Because df dx is going to be, so that's the derivative of sine 2x, sine of y over x. So what's df dy? F of y is just going to be sine of y. So the derivative of sine of y, that's cosine of y. And dy dx, that's just the derivative of y with respect to x. That's the number 2. And if I now make the substitution, y equals 2 times x, you can see that I get the number 2 times cosine of 2x. So it's really the same thing that I got over here in this equation, the derivative of sine of 2x. That's the derivative of sine, plug in 2x, and then times the derivative of my inside function. So I hope that helps drive home what we really mean by df dy, taking the derivative of f just with respect to the variable y, then multiplying by dy dx. So both of these things, I've written them straight beside each other. They're both called the chain rule. You might call this the Leibniz version of the chain rule if you like. You use this one when you really want to keep the variables straight. And this one we usually just call it the chain rule. You might use this one when you're trying to really emphasize the composition of functions. Okay, and so what I want to do now, I'm going to show you some of these graphs. So let's look at the graph of sine of x. There it is. And superimposed on that, I'll look at the graph of sine of 2x. So there we go. And you can see that with the sine of 2x graph, the frequency, it's twice as much. That graph is speeding by twice as fast. So I'm going to focus on the point x equals pi over 2. I'm going to show you the tangent lines to sine of x and sine of 2x. There we go. And if instead of multiplying by 2, if instead I had just looked at the tangent line with slope cosine of 2x, because that's what we say when we first see this, why do I need to multiply by the derivative of the inside function? Why can't I just take like f prime of y? If I only had that line with slope cosine of 2x, here's what it would look like. That's the green line. And you can see it's not a tangent line at all. So in order to actually be the tangent line to the function, in order to actually capture the rate of change of that movie playing twice as fast, we need to take not just the derivative of f at the point y, not just cosine of 2x. We also have to multiply by the derivative of the inside function.